So they can come click on this.
So, what makes a molecule polar? Well, two things. First, asymmetrical electron distribution around the molecule. You can't have a polar molecule made up entirely of the same element because those atoms will all have the same electronegativity, and thus the electron distribution would be completely symmetrical. Electronegativity is usually thought of as how much an element wants electrons around it, but I think it's more about how much electrons want to be near that element. If electrons were 13-year-old girls, fluorine would be Niall-Horan. They'll do anything just to be near it. Why? Some simple periodic trends.
Here they will answer this question in their own words.
Negativity increases from left to right because there are more protons in the atoms, and more protons means more boys in the band. Meanwhile, it decreases as you move from top to bottom because as the crowd of electrons gets bigger, they start to shield each other from the effects of the protons. What I'm trying to say is that electrons are hipsters. If a bunch of other electrons are into that thing, they're less interested. Now, there are a number of other factors here, but just like the relationship between tweens and their latest boy band fixation, it's complicated and weird, and you probably don't want to think too much about it. But in this nice little map, you can see that the trend is pretty clear. The upper right is where all the superstars of electrofame are. Oxygen, nitrogen, fluorine, chlorine, and bromine are basically the one direction of the periodic table. So for polarity to occur in a molecule, you have to have two different elements at a minimum, and the difference between their electronegativities has to be 0.5 or greater. If that's the case, the outer electrons spend enough extra time around the element that's more electronegative that chemists label the molecule polar. The result is a partially negative charge on the more electronegative part of the molecule and a partially positive charge on the less electronegative side. Now, in extreme cases, like if the electronegativity is greater than 1.6, then we end up with two ions in the same molecule. This isn't what we're talking about here when we talk about polar molecules.
This is what we call an ionic bond. We will talk more about this next week in class.
We're talking about differences between 0.5 and 1.6. Another requirement for polarity, you've got to have geometrical asymmetry. CO2 here has the charge asymmetry locked up, but because the molecule is linear in a straight line, it's a kind of symmetrical asymmetry. The same thing goes for CH4 with its tetrahedron of weakly electronegative hydrogens around a more strongly electronegative carbon. These molecules have polar bonds, but the molecules themselves are not polar because the symmetry of the bonds cancels out the asymmetry of the charges. In order for a molecule to be polar, there has to be a dipole moment, a separation of the charge around the molecule into a more positive area and a more negative area. Lots of molecules are asymmetrical in both electronegativity and geometry. Those are our polar molecules, the asymmetrical beauties of chemistry. Look at them all. They're so quirky and weird. We've also got a system for indicating where their charges are. We draw an arrow with a plus sign at the tail pointing toward the negative side of the molecule. Little lowercase delta plus or delta minus by the individual atoms signify a partial positive or partial negative charge. Liquids made up of polar molecules are really good.
So once they have completed it, they submit all of their answers and show up there. Then, to check their scores, I can go to My Classes, click here, and then here is showing what they watched, and then I can download the grades. And we'll go into a spreadsheet. Here are all the questions. You can grade the right response one here. And yeah, that's it.